Hi, this is Dr. Schaus again. For Module 3, we're going to be talking about the proposed Norfolk storm surge barriers case, and this PowerPoint presents some foundational information for that case. We're going to be talking about different tidal fluctuations, storm surge, and then barriers and how this contributes to resilience within an area, and then the proposed Norfolk flood barriers and some other ones that have been proposed for our region. So actual tidal fluctuations are influenced by the moon and the sun, the gravitational pull of the moon and the sun, but the simplified version of this is actually kind of a gross simplification of how the tides actually vary. I would encourage you to check out the two videos in the supplemental section, How Tides Work, and then Global Ocean Tides. These videos, I think, do a really good job of helping to illustrate this. The moon and the sun's pull does impact the water, but not in such a simple way because continents get in the way. And so as the water's moving around, it then comes into a barrier and there's frictional forces. In reality, the waters in certain oceanic basins will rotate in a clockwise or an anti-clockwise way. Such as this in the North Atlantic. We have low tide here in the darker areas, high tide in the lighter areas. So this would represent kind of a fluctuation of the bulge of the water, and then 6 hours later it's going to fluctuate around and back toward the same areas. And so this is kind of a better description of how the tides work. Again, this is graphically illustrated in the Global Ocean Tides videos to help illustrate this. Now, there are three main categories of tidal fluctuations at a site because, as the How Tides Work video talks about, no one site is exactly the same as the other because of the configuration of the shoreline. You can have one where one side of a peninsula there might be a 6-meter fluctuation and the other side is a 50-meter fluctuation. So But the three main categories are usually we see a semi-diurnal tide. 2 high tides, 2 low tides in a typical 24-hour period, and they're basically the same. The 2 high tides are roughly equivalent to each other. The 2 low tides are roughly equivalent to each other. In contrast, on the west coast of the United States, many areas have a mixed semi-diurnal tide. You have 2 high tides and 2 low tides during a tidal day, but the high tides are not of equal height. In this illustration, the higher high tide is about 3.5 feet above the standard datum, whereas the lower high tide might only be about 1.6 feet above that high tide level. And then for the lower low tide, in this particular one, it's -4 feet, which is a huge negative tide. But the higher low tide would only be about 1.5 feet into the negative. So depending on whether you hit the higher high tide or the lower low tide, that's going to have a big effect. And it's because of the local topography in that area. Some areas, especially islands, will have what we call a diurnal tide, only 1 high tide and 1 low tide during a daily period. This course does not really focus on those. Oceanography focuses on those. My main point in bringing this up is that organisms and people get used to a typical tidal range for their location. They're used to, this is about as high as the water goes, this is about as low as the water goes, and that's what impacts species distribution. A good example is the Rocky Shore zonation. This would be a typical area on the Pacific coast. You have the area below the low tide zone where it's never covered and uncovered by the tides each day. That's called the subtidal area. The organisms that live there are used to being always submerged by the tides. In the intertidal zone between the low tide zone and the high tide zone, the organisms that live there are used to being covered and uncovered by the tides once or twice a day, depending on the location, depending on how high. The higher you get, the drier you get, the lower you get, the wetter you get. And when you're up in the splash zone, the limpets and the periwinkles that live there might only get splashed by water a few times a month, but that's enough for them to be able to survive, and they can live in that type of habitat where other organisms cannot. And then above that zone is the supratidal zone, or the terrestrial area. Now, some factors will influence this. We have our predicted high and low tides. This is, the blue is a predicted semi-diurnal tide for Wilmington, North Carolina. And as you can see, the high tides and the low tides are roughly equivalent. The high tides, the two high tides each day and the two low tides each day are roughly equivalent to each other. However, right about in the middle of the graph, you notice that the green starts to spike up from there. And the explanation for this is that there was a large storm that was coming ashore. And the surge from that, the added wind, then pushed an extra mass of water toward the shore, and this caused the high tides to be even higher. You still see the tidal fluctuation, but the high tides are even higher. The low tides are also higher. In certain locations, this is known as wind tides, and it's tides is in quotes because it's not really a tide. For example, up in the Albemarle Sound, any wind blowing out of the southeast is going to push the water up to the north end, past Currituck and up into Back Bay and into the Intercoastal Waterway, and this can lead to flooding in areas that they normally don't get them, just simply because the water is kind of piled high in this one part of the sound. And this is an example of a flooding event in the southern part of Virginia Beach that was as a result of these wind tides, causing the water to be probably about 3 or 4 feet higher than normal, and flooding roadways that typically don't flood all that often. So this really is a good example of a storm surge. It just happens to be directionally oriented so that wind out of a certain location, they can expect a high tide. But during a storm event, you can get tides that are much higher than high tide levels, and this can lead to a lot of water coming ashore, causing tidal damage and things like that. And so our session today focuses on storm surge and what some local communities are proposing to do to impact that storm surge. And then you are going to investigate a certain aspect of that to determine, are there negative environmental consequences? Is this sufficient to be able to hold back the tide and protect dwellings, habitats, things like that? And that's what you'll be investigating. So a good example of this is in the Netherlands. The habitats of the Netherlands are highly human impacted and highly managed by people. This is an example of one of the canals that has a major storm surge barrier across the canal, where this gigantic structure, as tall as the Eiffel Tower, you can see it's clearly longer than one of those cargo ships in the background of the photo. These shift into place, and then that holds back the tide at the highest of the high tides when a storm surge is occurring. Now, similar sorts of plans have been proposed for the city of Norfolk, a combination of seawalls, dikes, levees, berms, and some of these stormwater protection structures. Now, we're going to focus our attention on the Hague, which is just a little bit to the left of where the number 1 is in the downtown section of Norfolk, and then the storm surge barrier that's proposed for the Lafayette River, which is the Lafayette River is number 3, and the storm surge barrier is the blue line located all the way to the left of that. Now, you can also consider some of the others and investigate some of the others on this Resilient Norfolk website, such as the Broad Creek one, number 4, and then some of the non-structural mechanisms that they're looking at, such as number 5, or Pretty Lake up at number 2. Now, other local areas have similar proposals for storm surge barriers. This is the one for the Rudy Inlet area of Virginia Beach. Again, this type of structure would rotate into place, and a combination of that and localized seawalls plus shoreline replenishment would then keep the ocean at bay during hurricane events and things like that. This is what they've proposed for the Lynn Haven Inlet, a series of several channels that boats could get through, but during storm surge they would basically raise the barriers, block that area off, and protect the houses and habitats that are located inland from this. At least this is the proposal. So to do this week, first of all, check out the Resilient Norfolk interactive website. There's a video in there I want you to take a look at, and I want you to kind of click on all the different aspects and see what the different plans are for the 5 main areas of focus for this. I want you to specifically look up the plan that we have for Norfolk, or for the Hague, and then look at the plans for Norfolk in general. I'd like you to focus on the Lafayette River, but I want you to pick a specific area of this and consider the environmental aspects related to this. Maybe that would be the specific flood barrier. Is it affecting fish migration? Is it affecting erosion? Is it going to have effects on habitats and organisms there? What about the non-structural features, such as raising up houses? A couple of the videos today on the Sea Level Rise Sojourn series talk about and show examples of houses that have been raised up. Plus some nature-based features, adding marshes, adding oyster reefs, things like that. Are they going to be effective enough? You're going to research one of these in detail for your annotated bibliography, and then I want you to focus on whether you think that this plan for Norfolk in general is going to be successful in your discussion board post. All right, thanks.